Alright, now that I've looked at all these exams and realized, amongst other things, I'm going to pull something out here. Hope the computer doesn't blow up. Mathematics and engineering use a common language, and sometimes you've got to marry that language with English. So I'm going to go through this exam giving down what my expected preferred answer was, if I can actually do this review start inking thing here. Never done this in Word before, but I'm going to go through, I'm going to talk about where the best answer in my opinion was, and where I'm taking partial credit, and you're all going to be doing this anyway. This is not about this test. This is about you grabbing onto some knowledge here that you're going to carry forward long after whatever occurs. Learning how to pick out some keywords and realize what some basic mathematical information means, and learn to put things into some context. So let me go through this. Number one, how quickly a bridge would be spinning. So somewhere in there you would really be interested in, I hope, torque equals I, moment of inertia, the real moment of inertia times the angular acceleration. That, of course, would lead to W, or the angular velocity, is equal to the initial angular velocity plus alpha t. Of course, that would lead to some spin angle is equal to the initial spin angle plus W naught t, the initial spin times time, plus 1/2 AT squared. Now, once again, all those formulas are not on there. I'm going to try to close this up if it'll take it. So the only one that was there was here. Now, how quickly F equals ma, yeah, I guess. But the spinning part is where I was looking for, that you can know that there is F equals ma and torque equals I alpha. Again, you've been pointed out to Professor Lewin's lectures. And if not, then you have them when you go forward, in whatever language you choose. All right. The torsional spring. This one I would guess a lot of people did this. 1/2 kx squared. That is Cook's law, basically, or the sum of the energy. So that's basically potential energy in a spring. But the key word here is the amount of energy, and energy is the same as work. And I think I talked a little bit about work stored in a spring or in some torsional system equals the moment times d theta, especially if you're looking at work having units of foot-pounds, and this also having units of foot-pounds. So that was the answer I expected there. The best stress-strain relationship, it's best to do this, strain and stress, and that is P over A, and that is delta L over L. This is deflection, or delta L. I guess delta L equals P, the force times the length divided by the area times the modulus of elasticity. Please don't just remember this. Please remember the stress strain of steel, the stress strain of concrete, the stress strains of soil, it being the stiffness and having units of psi, because this is unitless. Number 4, integration. What formula integrates the shape equation? So you're looking something that had both integrates and the shape equation, perhaps with respect to x to calculate a deflection angle. So the deflection angle, theta, equals the integral of 0 to x of m dx over ei. All right, and what you're going to see here is this is the one that leads to the next step. The fourth order integration takes you down to the actual formula for the deflection. So this is deflection angle. You use deflection angles from survey. The maximum stress across a face would be shear. Now you know that V over A is the average shear stress, but you should know that the max of any shear stress is V, the shear force, divided by the first moment of the area over the moment of inertia of the section, and times the width of the section. And how does that look like? Well, if you're looking at the cross section of a beam, the first moment of the area is the area outside, so you're going to take the area times this distance, so area times distance, that's the first moment of the area. And this moment of inertia is of the whole thing. So basically this is going to get you the maximum stress. If I looked at it in profile, you've got no shear along the sides, maximum shear, and on the average we calculate 40% is what we use. So that one's VQ over IB. What formula calculates the amount of energy of a falling piece of concrete? Falling, kinetic, 1/2 mv squared equals kinetic energy. Falling and spinning, you would add that to the rotational kinetic energy. Energy stored in a spring, we talked about that in potential energy equals 1/2 kx squared. That again ties you to stress strain, but in this case it is your delta x, and this is force, which is the spring constant, times x, and so the area under that is 1/2 kx squared. Number 8. What formula would you need to calculate the potential overturning force of our car rolling around a curve? The overturning force, if I come in at you, right, and I'm going around a curve, it is going to be the centripetal and centrifugal force here. It is v squared over r gets you the a, and of course mass times acceleration equals the force of turning, more or less, or centripetal. Centripetal. All right, so the fact is weight is holding you down, something else is spinning you over. What formula for G is wrong? Of course, G, the formula for the acceleration constant, is equal to big G mass of the earth over r squared. The second mass in front of each of them makes that weight. Number 10, formula you pair with CAD. Basically, it's force times distance orthogonal. In other words, if you're in CAD, most likely you might be able to do this. You've got a line of force there, and you want to know the point here. You do force line perpendicular to, you list that, and that gets you the torque. That's the one I meant. And you really do that a lot. That's probably the way when you're in CAD you do moments a lot. It's force times orthogonal distance. When you strip the force vectors and the moment vectors, moment equals the magnitude of the force, the magnitude of the radial vector, times the cross product of the force vector, the cross product of the radial vector and the force lambda vector. In other words, these will each be one long, and basically you're yielding how close to 90 degrees those two things are. So that was this one, stripping out the vectors, because you strip them out here. We know that vector force is equal to the magnitude of force times lambda sub f, the unit vector describing the direction of the force. What formula when divided by weight gives you the elevation head? You'd have to know the elevation is head, and you have to know what it is. It's mgh over mg, or the weight. Energy, foot-pounds of energy divided by pound of material. Number 11, the bending stress in the outermost fiber under a bending load is either mc over I or m over s. This gives you the point at any place. In other words, if I'm in a structure and I've got a bending moment with a neutral axis and compression and tension, if I want to know what the stress is right here, I use the c from here to here. But usually you're interested in the outermost. That's the same as m over s. Number 14. Formula for the shape, 1 over rho equals how much it's being twisted by its resistance to torsion or twisting. What formula is used to calculate the maximum deflection of a simply supported beam? Deflection equals 5WL to the 4th, 384 EI. Uniformly loaded, there's our uniform load. You could also have written this, of course, 5 big W L third over 384 EI, assuming a constant modulus of elasticity and a constant moment of inertia. On to 16. I guess this will be 20 minutes. What formula is used to determine what allowable stress is in a column? In a column, F allowable axial should be less than or equal to some constant times the yield stress of the steel. And that constant is a function of the slenderness ratio. In other words, the more slender it goes, the lower the constant goes. You know that you don't get more than 60% ever. What formula expresses shear as a function of uniform load? Again, as a function of uniform load, there was only one that said shear at X is equal to shear initial, or shear naught, minus the load, the area under the load curve. There's probably only one that had load on the right side of the equation. That was it. What formula for moment is the most descriptive? Realistically, believe it or not, it's R cross F. It's the most extensive and descriptive. I'm out of time. We'll continue in the next 10 minutes. I hope you'll look at these and we'll figure out for you a way to resubmit to adjust your grades. Thanks for listening.